Today's experimental math seminar speaker is Professor Peter Cameron from St. Andrews University, who will talk about finding the jewel in the lotus. As usual, please mute yourself unless you have a comment or question. Then go ahead and interrupt. Go ahead, Peter.
Thank you very much. I hope everyone can see my slides and can hear me okay. Let me know if you can't. I really don't mind being interrupted if there's something you don't understand. Good. And I know it's Halloween. I haven't prepared anything scary for you, so I just hope that it's not scarily difficult mathematics. Anyway, here we go. A little bit about me to start off. It's more than 50 years ago since I got my PhD. I've been in universities ever since, but my current university has just decided that it's time for me to retire, so I will be retiring next year. But I intend to carry on doing mathematics. St. Andrews is the third oldest university in the Anglophone world, 1413, and I've always enjoyed groups and graphs, and so it was a real bonus for me when in 2021, when we were all locked down in the pandemic, Ambat Vijay Kumar from CUSAT in South India, in Kerala, invited me to lead an online research discussion about graphs on groups. So I did that, and the result of that was 50 people joined this research discussion. So I had people all over India getting interested in these problems, working away at them, and sending me things saying, I've done this, what should I do next? So it's really been keeping me busy, this stuff. Anyway, I'm going to tell you about one thing that came out of this, which is experimental mathematics, in the sense that maybe if I were smarter, I would be able to see what the answer is, but I'm afraid I'm not. So all I can do is get the computer to work out a few examples for me and see if I can spot the pattern. So that's what I'm going to tell you about. But first of all, I want to tell you a bit about what sort of graphs on groups I'm talking about here. But if you want to know more about this project, the London Mathematical Society newsletter, October issue, will have an article about this research discussion and its things that have come out of it. So you may be interested to take a look at that. Anyway, if you say to people graphs on groups, they think, oh, Cayley graphs. Cayley graphs are not what I'm talking about here. I'm doing something a little bit different, as I will explain. I want graphs that somehow are built out of the actual structure of the group. So the prototype example, the most famous example and the easiest one to think about is the commuting graph of a group. So the vertex set of the commuting graph is just the group itself. You take two vertices, x and y, you join them if they commute. In other words, if xy is equal to yx. So that's a nice simple definition of a graph. It goes back to 1955 in one of the most famous papers in group theory by Brouwer and Fowler. In 1955, they proved that if you have a simple group of even order, well, if a group has even order, it contains an involution, an element of order 2, and you can work out the centralizer of that, the things that commute with that involution. And if you specify the involution centralizer, then they showed there are only finitely many simple groups that can arise. And I would say this was perhaps the first step towards the classification of finite simple groups, because if you look at the papers that went into the classification, there are maybe hundreds of papers classifying particular simple groups by the centralizer of an involution. And this all grew out of the work of Brouwer and Fowler. But I should say one thing. I've said here simple groups of even order because in 1955, we didn't know that all simple groups have to have even order. was a conjecture of Burnside, but it wasn't proved until Feit and Thompson in the early 60s, and that was the first of these really, really long proofs that started coming up in finite group theory. But anyway, so Brouwer and Fowler proved that. The word graph does not occur anywhere in their paper. Graph theory wasn't really a subject back then. When I was a student, I didn't learn graph theory or indeed any combinatorics in my undergraduate degree. It didn't exist. It wasn't a subject. But anyway, they don't use the word graph. What they do instead is they say, take two elements of the group. You want to find a chain of things, chain of elements between them, such that each pair commute. Now, you could do that very easily because the identity element of a group commutes with everything else. So you could just take one step to the identity, one step back to the other element, and you've learned nothing. So they said, leave the identity out. So basically, they were taking the induced subgraph of the commuting graph on the non-identity elements of the group. And they were using that. And their arguments are very graph theoretic if you read them. With hindsight, they were doing graph theory, but they didn't call it that. I have to say okay. Yeah, right. Come on, wake up. There we go. So I'm going to define a couple more graphs that will come into the story. There are many, many of these graphs now. People have been getting very busy and inventing different graphs on groups, but I only need a few here. So here are some. There's one called the power graph that was introduced about 2000. X and Y, two elements of the group, are joined if one is a power of the other. So if either X is a power of Y or Y is a power of X, you put an edge joining X to Y. And of course, if you think about that graph, it should really be a directed graph, shouldn't it? You should put an edge from X to Y if Y is a power of X or something like that. Well, in fact, we know that the power graph determines the directed version up to isomorphism. If you have two groups that have isomorphic power graphs, then they must have isomorphic directed power graphs. But that can happen. There can be different groups that have isomorphic power graphs, but at least we don't have to worry about the directions. So we can regard it as an undirected graph. And there's one more, which is called the enhanced...
Sorry, Peter. Who was the first one to realize that it's really a graph implicit in the...
it was me. It was me.
Oh, it was you? Okay.
Yes. What happened was Shamik Ghosh, who was one of the people working on this, came to the British Combinatorial Conference, and he asked a question which was basically, what can you say about two groups that have isomorphic power graphs? But you can clearly say more if they have isomorphic directed power graphs. You can learn much more from that. But I was able to show that that implies isomorphic power graphs. So you don't lose anything just by considering the power graph. So it's quite a nice theorem. It's quite a nice little argument. And now recently, Daniela Bubaloni in Italy and her student have turned this proof into an algorithm. So there's a polynomial time algorithm to put the directions on the edges of the graph. If you're given a power graph, you can figure out the directed power graph efficiently. Anyway, so there's the next one is the enhanced power graph. So this is the power graph with a little bit more. What we do is we join X and Y if they are both powers of some element Z, right? So X is a power of Z, Y is a power of Z. Sorry, I should be calling it Z, shouldn't I? Apologies. I think I'll stick with the British version. But now you see, that gives you a graph, and it contains all the edges of the power graph, because if Y is a power of X, then you can just take this third element to be x itself. X is a power of x, y is a power of x. So if two elements are joined in the power graph, then they're joined in the enhanced power graph. So it's a little bit bigger than the power graph, but it's going to come into my story that in some sense, it's not very much bigger than the power graph. They're fairly close together. Right, so we have those graphs. The power graph, the enhanced power graph, and let me look a little further at the enhanced power graph. If x and y are joined, they're both powers of some element, so they lie in the cyclic group generated by that element, but any subgroup of a cyclic group is cyclic, so the group generated by x and y themselves will be a cyclic group. So another way of doing it is to say we join x and y if they generate a cyclic group. And that's a nice condition that depends only on the group structure. So that's the sort of graph that we're trying to get at here. But once you've seen that, you say, oh, well, replace cyclic group by your favorite class of groups, abelian group, let's say. What do you get if you join x and y if they generate an abelian group? Well, if they generate an abelian group, that means precisely that they commute. So that will just be the commuting graph. So if you replace cyclic by abelian here, you get the commuting graph. You can go on to other classes too, but I don't want to do that. We have enough graphs to play with now, and I can pose my problem, my exploration, just in terms of these graphs that I've told you about. So let me just pause and say, does anybody have any questions up to this point?
I have a general question. Combinatorial group theory is a very old field. So do you have graphs implicit in combinatorial group theory?
Combinatorial group theory, well, yes, Cayley graphs basically is the answer to your question. But so for a Cayley graph, these graphs I'm talking about just depend on the group, nothing else. For the Cayley graph, you've got to have a group. You've also got to have a set known as the connection set. So you join two elements x and y if you get from x to y by multiplying by some element in the connection set. But you see, it depends on the connection set. Now, Cayley graphs are very important. The whole of combinatorial group theory, or they tend to call it geometric group theory these days. It's the same subject, but it's become a bit more geometric. But that subject is all about Cayley graphs. But my graphs here are really not Cayley graphs. So they're just purely reflecting some structure of the group itself.
Peter, can I ask a question? You haven't
Yes,
said
please.
finite. Yeah, so you're not assuming these are finite graphs, of course. Finite groups.
They were these graphs were just as well in the finite and the infinite case. But I'm only going to talk about finite groups here because well, there are some small problems that arise in the infinite case. For example, suppose you take the infinite cyclic group and you want to look at the power graph. So it's the additive group of integers. Is 0 joined to anything else? Well, everything to the power 0 is 0. 0 times anything is 0. So yes, maybe it should be, but then on the other hand, you might say that's cheating. So there are some difficulties that have to be resolved in the infinite. So to simplify things, I will stick to the finite here, right?
Okay, thank you.
Right. Okay, so now I already remarked that all the edges of the power graph are edges in the enhanced power graph, and also all the edges in the enhanced power graph are edges of the commuting graph, because the rule for joining in the enhanced power graph is that they generate a cyclic group. In the commuting graph, it's that they generate an abelian group. So we've got the beginnings of a hierarchy here. Only 3 graphs in it. You can add more, but 3 will be plenty for me. And as I said a moment ago, the power graph and the enhanced power graph seem to be fairly close together in a sense. And that is something that I'm going to use later on. So, for example, so one of the things that came out of this Indian business was I was able to prove with 2 co-authors in Kerala that the power graph and the enhanced power graph have the same matching number. that is, you ask for the maximum number of pairwise disjoint edges, it's the same in both of those graphs. And the argument for that is not a group theoretic argument at all. It's a graph theoretic argument. It's a sort of alternating chains argument that you use over and over in matching theory for graphs. So these graphs are fairly close together. And at a certain point, I'm going to say, look at the edges that belong to the enhanced power graph and not the power graph. But that'll come up in a bit. That's what I'll be looking at. So anyway, in general about this project, what are the aims of this project? Well, I think there are three aims. First of all, we can define classes of groups from the graphs to find them. One way of doing that is to say, which are the groups for which, let's say, the commuting graph is a perfect graph or a caudal graph or something like that. There are some things known about this sort of question, but not everything. These do define interesting classes of groups. Or the other thing we could do is we could say, which are the groups for which this graph and that graph happen to coincide? We know that one's contained in the other, but for which are the groups for which they coincide? I'll give you an example of that in just a moment. Also, you might be able to prove new theorems about groups by using these graphs. That's exactly what Brouwer and Fowler did with the commuting graph. And we have an example where we were able to improve an old theorem going back to Landau 120 years ago. We've got an improvement of it by looking at a certain graph defined on the group. So that's another thing that you can do with these. And the third thing, which is what I'm mainly going to be talking about here, is you might find interesting and even, let me say, beautiful graphs coming out of these groups. But as you'll see, it's not entirely straightforward to do that. Anyway, so those are the things that I'm going to, particularly the third one, that I'm going to focus on here. I must say that an awful lot of work has been going on. People take their favorite group, which might be the dihedral group or something like that, and say, now, let's look at one of these graphs, let's say the power graph of a dihedral group. What can I say about it? Work out all the parameters that you possibly can. Well, I must admit, I don't find that so exciting. I think that these three things that I've outlined here are more like what we should be doing. So I've been trying to push this view on my collaborators. Anyway, so that's something about this Graphs on Groups project. So I'm going to give you an example of how a certain class of groups, it was an already known class and they've been characterized, but they have a beautiful description in terms of graphs. Which are the groups for which the power graph and the enhanced power graph happen to coincide? So we know that the power graph is contained in the enhanced power graph. The edge set is contained in the edge set. What can you say about groups for which those are equal? Well, we can answer that question. Here's a characterization of them. They're precisely the groups in which every element has prime power order. One way around that's very easy to see. If there's an element whose order is the product of two primes, P and Q, then, there's a typo here, I'm sorry. If X has order PQ, then X to the P has order Q, and X to the Q has order P. They're both powers of X, so they're joined in the enhanced power graph, but they're not joined in the power graph. So if there was an element whose order was a product of two distinct primes, then these two graphs would not be equal. The other way around, I won't go through the argument, but it's very similar. So what do we know about these groups? Well, the first person to consider them was Graham Higman in the 1950s. He determined all the solvable ones. Suzuki in the 1960s found the simple ones, and indeed two of the simple groups that come up are two of the Suzuki groups. Suzuki found an infinite family of groups in the early 60s, and two of them happen to have this property that all the elements have prime power order. So these groups, by the way, I haven't said here, they're sometimes called EPO groups. EPO is an acronym for elements of prime power order. All the elements of the group have prime power order. So if you just think about groups of order 6 for a moment, the cyclic group of order 6 has an element of order 6, so it's not an EPO group. But the symmetric group on 3 letters is another group of order 6, and all its elements have orders 1, 2, or 3, so it is an EPO group. And so we knew the solvable ones, we knew the simple ones, but in 1981, Rolf Brandl published a paper in a, I would say, rather obscure Italian journal where he gave the complete classification, not using the classification of finite simple groups. He didn't need to use that. It was more elementary than that. But the only way I could get hold of this paper was by asking some Italian colleagues if they could find a copy in the library and send it to me, because the particular issue of the journal that has Brandl's paper in it is not available anywhere on the web as far as I can tell. Anyway, so I want to go on to the part
did you check it? Is it correct?
It is correct, yes, indeed, because what happened was, before I found it, I asked Natalia Maslova in Yekaterinburg. We were writing a paper together, and I said, can we actually determine this whole class of groups? Well, yes, we could, and together we managed to write out a proof. So I'm pretty sure that it's correct because we have our own proof of it. But I have been through Brandl's paper, and he seems to get it right as well.
So you have a different proof.
It's not so different, really. It's but yes, it is a different proof. We didn't know Brandl's proof when we started out on ours, and I believe that
does it follow immediately from the classification if you use the classification?
Not immediately, no. You still have to do quite a bit of work, because not all these groups are simple. Some of them can have abelian normal subgroups, so you have a bit of work to do. But because Brandl's paper was quite obscure, I think that encouraged various other people to tackle this problem themselves. They could see what Higman had done, what Suzuki had done. They said, can we give the complete classification? So there are a couple of other papers that do that, but I only found them later. Anyway, so what makes a graph interesting? Well, different people will answer that question differently. I like a graph to have lots of symmetry. Well, I'm a group theorist, so that's reasonable. Other people might ask for certain kinds of regularity condition, or being something like a cage, having large girth for the numbers of vertices and edges, or whatever. There are various reasons a graph might be interesting. But here was something that gave me a bit of a shock. A few years ago, my colleague Kolva Roney-Dougal and I were looking at a graph called the generating graph of a group, where you join two elements if they generate the group. Now, that's not one of the ones I've talked about so far, but that's the definition. It's fairly simple. So if a group can't be generated by two elements, this is a very boring graph. It has no edges at all. But fortunately, we know now from the classification that all the finite simple groups can be generated by two elements. So we're not short of examples. So we said, let's look at the smallest one. The smallest non-abelian simple group is the alternating group A5. It's a group of order 60. So construct the generating graph and ask how big is its automorphism group. And this is what came out, this shockingly big number. We were quite horrified. But it was just as well we were not doing the commuting graph, because the answer for the commuting graph is this number with more than twice as many digits. So something terrible is going on here. And took us a little while to figure out what it was, but there is an answer. But anyway, I'm looking for the jewel in the lotus. So there's a lotus flower. It's a very beautiful flower, but what happens to it? Eventually, the wind blows the petals away and essentially nothing is left, except that legend has it that just occasionally there's a jewel there, and if you might be able to find the jewel. So we're taking this graph, which is full of rubbish. The rubbish blows away, and with any luck, there will be a jewel left behind, a beautiful graph, and that's the graph that we're trying to find, right? So how do we blow the rubbish away? How do we get rid of it and get down to the jewel? Well, these are the villains, twins. What are twins? Well, in a graph, two vertices are twins if they have the same neighbours except possibly for one another. So there are two kinds of twins. You might have what you might call open twins. So X and Y are not joined, but their neighbour sets are equal, right? Or closed twins where X and Y are joined, their other neighbours coincide. So they have the same closed neighbourhoods in this case. You take the closed neighbourhood of X to be X together with all its neighbours. That includes Y. And if they're closed twins, that's equal to the closed neighbourhood of Y also. Well, the two different types of twins are not actually going to matter very much for me, so you don't have to remember that. Just remember that there are twins. And why are twins bad news for us? Well, first thing is, these graphs that I'm talking about, graphs defined on groups, tend to have lots of pairs of twins, because if you have two elements that generate the same cyclic subgroup, suppose X is an element of order 5, then X squared, X cubed, and X to the 4th all generate the same cyclic subgroup that X does. And then any reasonable graph defined on the group, those vertices will all be twins. So there tend to be lots of twins in these graphs. And why is that bad news? Well, being twins is an equivalence relation. All pairs in an equivalence class are the same kind of twins, all open twins or all closed twins. That's not hard to show. But here's the real killer. If you take an equivalence class, permute it any way you like, fix everything else in the graph, that's an automorphism of the graph, because these twins are in exactly the same relationship to the rest of the graph as one another. So however you permute them, that'll just map edges from them to the rest of the graph to other such edges, and they'll be fixed. And the rest of the graph is being fixed anyway. So you get a symmetric group on each equivalence class. And these symmetric groups tend to be pretty large. N factorial is a fairly rapidly growing function. So that means you get lots of these rubbish automorphisms that are telling you nothing about the group structure. All that you know about the group structure from these automorphisms is that all those vertices are twins. They have the same sets of neighbours. And we knew that anyway. So they're not interesting automorphisms. So our job is to get rid of the twins. Right, so how do we get rid of the twins? Well, there's this process of twin reduction that we use. So twin reduction says, choose a pair of twins, identify them, so turn them into just a single vertex, or if you prefer, just delete one of them and keep the other. Right? So that's one step in the process. Take a pair of twins, reduce it to one vertex. There might still be twins, so go on doing that. But there is a slight problem. I said the twin relation is an equivalence relation, and you get these equivalence classes, and your first thought might be that if you just shrink all the equivalence classes down, that'll do the job. But it's not so simple. Here's a little example. Here's a graph that has a pair of twins. The two red vertices on the left are twins, you can see. they're closed twins, in fact. They're the neighborhood of each of them, apart from the other one, is just this single vertex in the middle. So they're closed twins. So do twin reduction on that pair, we get this graph, the path, the 3-vertex path, because these two have now turned into just one vertex. But now we've got some more twins. Suddenly this vertex has become a twin to the vertex down the far end. So we have to go through another step. We have to identify those two, fold the path over, and just get an edge. Now, finally, those two blue vertices are twins, so you have to go one step further and reduce to a single vertex. So twin reduction is not just collapsing the equivalence classes. You may need to go on and do more things after that. So it's a process, but at the end of it, you wind up with a graph that has no pairs of twins. And the good news is that the graph that you get by doing twin reduction till there are no more twins doesn't depend on the way you did the reduction. You see, you can do this reduction process in many ways. Might be lots of pairs of twins, reduce one here, reduce one over there, keep going. Doesn't matter. However you do the reduction, you will always wind up with the same reduced graph, the same twin-free graph at the end of the process. So that's the nice thing about twin reduction. We can just do it. And since I've been dealing with graphs on rather large groups, it's better to get the computer to do that. And it seems that the most efficient way to do it is first to collapse all the open twins, then another pass through, you collapse all the closed twins, and then another pass through, you collapse the open twins again. And after just a few passes, usually, you've got rid of all the twins. You can see in my little example, we collapsed closed twins first, then open twins, then closed twins again. So this seems to be the way to go if you're actually doing this process for real. Anyway, we reduce the graph till it has no more twins. Now, I have to make a little detour and tell you about cographs. This is a class of graphs with many different names because it was rediscovered by many different researchers, and some call it complement reducible graphs. Some call it, for reasons that I'm not quite clear on, hereditary Dacey graphs. But there are various names for it. I will just use the short term cograph. So a cograph is a graph that contains no induced 4-vertex path, right? So that's the simplest, cleanest definition of them, but it hides the immense amount of structure that this is giving you. A cograph is a graph that you can build up from 1-vertex graphs by 2 operations, disjoint union and complementation. So you can take a bunch of vertices, disjoint union, complement that, you get a complete graph. Then you can build another complete graph here. Then you can complement those. You get a complete bipartite graph, and on and on and on. And any cograph can be built by this process. Third condition is every induced subgraph is either disconnected or has disconnected complement. Now, of course, if a graph is disconnected, its complement is connected, but the graph and its complement might both be connected. But for cographs, one or other is disconnected. And then if you just look at that one, it's disconnected. So take its complement, and then you can take the reduction process like that. But the reason it's interesting to us here is the fourth one. If you do twin reduction on a cograph, it terminates with the 1-vertex graph. So cographs are precisely the graphs that collapse to a single vertex when you do twin reduction. And if you go back and look at my example, you see this graph is a cograph. It's got no induced 4-vertex path. It's only got 4 vertices altogether, and it's not a path. So that's a cograph. So the theorem tells us that's going to reduce to a single vertex when we do twin reduction, and you saw that it does. So cographs are the things where twin reduction collapses into a single vertex. Well, that means all the petals have blown away and we found nothing interesting. So cographs are not the things that I'm looking for. But so this is where the experimental mathematics comes in. So 3 Indian colleagues, Sushrita Biswas, Ansuman Das, and Hiranya Kishore Dey, and I did this work. We said, we want to give ourselves the best chance of finding something interesting. So our strategy will be, first of all, start with simple groups. Simple groups, any group theorist will tell you simple groups are the most interesting, perhaps almost simple groups. So, I mean, the alternating group is simple, but I don't rule out the symmetric group as being an interesting group. So we might want to take the symmetric group instead. So we start off with groups like that. There are not too many of them, so we can explore. And also, what we're going to do, we want our graphs to be fairly sparse. So we will use what we gave the name the difference graph to. So I briefly mentioned this before. You take all the edges in the enhanced power graph, which are not edges of the power graph. So you take the graph with those edges defined on the group, right? So that's it. Pick your group, let it be simple, probably, and then make this difference graph. The edges are the edges of the enhanced power graph, which are not in the power graph. Then do twin reduction on that, and we reckon that the chance should be fairly good that you will find something interesting. So we did some experimenting on it, and so now I want to tell you about the results. So the first couple of things that happened were entirely expected. So the first possibility is, suppose we chose a group where the power graph and enhanced power graph happened to be equal, then the difference graph would have no edges at all, and twin reduction would just in one go take it down to a single vertex. So that's not going to be interesting. But we know all the simple groups like that. This comes out of the work of Suzuki. Here they are. There are exactly 5 groups PSL2Q, 2 Suzuki groups, and the group PSL34. So it doesn't matter too much what these are, but these are 8 of the small finite simple groups. And if we do this procedure, make the difference graph on one of these groups, do twin reduction, you will end up with just a single vertex. If you build the difference graph, it will be a null graph and you won't have anything to do. The second case is where the difference graph is a co-graph. So when you do twin reduction, you'll get down to a graph with a single vertex. Now, there isn't a characterization of these. This is a problem that's not completely solved, but so with some other Indian collaborators, Pallavi Manna and Ranjit Mehtari, we looked at this question. We proved various things. There are some PSLs and some Suzuki groups beyond the ones that are EPO groups. So, but why can't we just determine them all? Well, I'll tell you. If Q is a power of 2, then so Q has to be a prime power in these groups. If it's a power of 2, then the difference graph is a co-graph if and only if each of Q plus 1 and Q minus 1 is either a prime power or the product of 2 distinct primes. Either one or other of those 2 things should happen. Now, if you start trying to figure out what happens, that happens surprisingly often. So if we just take D equals 3, for example, this is the famous case because this is the Catalan conjecture. 2 cubed plus 1 is 3 squared. 2 cubed minus 1 is 7, which is prime. When we go to 4, 2 to the 4th plus 1 is 17, which is prime. 2 to the 4th minus 1 is 15, which is 3 times 5, product of 2 primes. And there are many more like that. 23 is an interesting case because it's bound up with the Golay codes. 2 to the 23rd minus 1 is the product of 2 primes. 2 to the 23rd plus 1 is also the product of 2 primes. But so these are all the ones below 200 that have this property. And you see there are quite a few of them. And you ask a number theorist, can you tell me all the powers of 2 for which this happens? They'll say, no, sorry, we can't do that. So it's an unsolved problem as yet. And there are similar conditions for PSL2Q for odd Q or for Suzuki groups. Suzuki groups Q has to be a power of 2, so it's a little bit more limited. But there are some number theoretic problems to solve before we know the answer to these questions. Are there infinitely many is something that you might very well want to know. Well, even that number theorists can't tell us.
They cannot prove it, but do you have a feeling, intuition? It's probably...
I would conjecture that there are only finitely many, even though there would be rather a lot, because you see there are all this many below 200. I would conjecture that there are only finitely many, but I'm not a number theorist, so my conjecture probably doesn't actually count for much in the scales. Okay. Case 3. Now here's where it starts getting a little more interesting, but this is absolutely bizarre. We didn't expect this at all. Case 3, twin reduction takes you down to a graph which has a lot of small components. And for these two particular simple groups, PSL2Q for Q equals 23 and 25, the components in both cases are K5 with the edges of a P4 removed. And there are 253 of them in PSL223, 325 in PSL225. And I'm afraid I really don't know why. And in particular, I don't know why you get the same components, isomorphic components for these two groups. I can't see any good reason why that should happen. But this is a bizarre situation. What it suggests to me is that, in fact, the wind hasn't blown hard enough. We haven't blown all the rubbish away yet, because I think this counts as rubbish. We don't want this kind of thing. So we might have to think of another kind of reduction. But anyway, on to case 4. And here at last we find something nice. We get just one connected component. And its automorphism group is exactly what you'd expect. And often it has very large girth. So our favorite example is the Mathieu group, M11. This is a group of order 7,920. So we start off with a graph on 7,920 vertices. Twin reduction takes us down to just 385 vertices. That's a big reduction. And you take several stages of twin reduction to get there. But it's a bipartite graph, and the bipartite classes have size 165 and 220. It's semi-regular. All the vertices in the class 165 have valency 4. The ones in the class 220 have valency 3. Its diameter is 10 and its girth is 10. Now 10 is quite a large girth for a graph of that size. So it's not record-breaking or anything, but it's a quite remarkable graph, I think. And its automorphism group is the group that you started with, M11, and that's very pleasing. So here we reckon that we've struck lucky. And there's one more case where we found something nice, and that was the group PSL33. This is essentially the automorphism group of the projective plane of order 3. And what we get is a graph which is geometrically built out of the projective plane. And I think this should be interesting to finite geometers, this graph. I don't believe it's been investigated. So the number of vertices is q squared plus q plus 1 all square, where q is 3 in our case. But the construction works in general. So the square of the number of points in the projective plane, well, actually the vertices you can identify with the pairs, a point and a line in the projective plane. Now, there are two kinds of point-line pairs. The point might lie on the line, that's a flag, or the point might lie off the line, that's an anti-flag. So the point-line pairs fall into two classes, the flags and the anti-flags. The graph turns out to be bipartite, and those two sets are precisely the bipartite blocks. There's a simple rule for incident. If you take a flag and an anti-flag, so the flag has a point P and a line L, I've drawn it here in the picture, P and L form a flag, M and Q form an anti-flag, and the rule for joining them is that P should lie on M, so the point of the first flag should lie on the line of the second, and the point of the second flag should lie on the line of the first. So that's a nice construction of a graph. And it works for any Q. You just take the projective plane over any finite field and you get one of these graphs. We don't know whether it comes from a group or not, but the graph is always there and probably has nice properties. It is semi-regular, and the valencies in the two bipartite blocks are q squared in the flags and q plus 1 in the anti-flags. And that's not quite all. Other kinds of things can happen. M12 gives you a graph with two components, both rather beautiful graphs with automorphism group M12. But other things can happen. One of the stranger examples is the symmetric group S7, where we get one big component with 322 vertices, 7 components with 35 vertices. So a bit of a mixture. So we really need to understand this twin reduction better, especially on these kinds of graphs on groups. So there's plenty more to do. We've only done the first dozen or so simple groups. We can look at further ones, but there are other types of graphs. You could look at the power graph or the enhanced power graph or whatever, or other difference graphs. And you could look at groups other than simple groups. So anyway, here are the papers that I've been essentially discussing in this talk. This is the paper with what I've really been talking about. This is the one with which groups have power graph or cograph. This one's about the theorem about the matching number of the power graph and enhanced power graph being equal. And this paper here in the International Journal of Group Theory is just a compendium of what I knew at the time about graphs on groups. So as you can see, it's quite a long paper. It's almost a monograph. So if you want to get interested in this stuff, that's the place I would recommend you to start. And I believe my time is up, so I'll just say thank you for your attention.
Thank you very much for a very enlightening talk. Are there any questions to Peter? Please unmute yourself and ask. We have a quick question. You mentioned the Golai code. So
Yes.
these new constructions, can they lead to new, interesting, error-correcting codes?
Well, that would be nice. I don't see how to do that yet. Maybe some idea will come to me as I carry on with this project. But at the moment, that's just... It would be nice if it happened, but I don't at the moment see how to do it that way.
Thank you.
I have a question.
Yes.
This is Victor Miller. When you do twin reduction on your graphs, if you
Yes.
carry along the original labels, then that gives you an equivalence relation on the elements. So does that equivalence mean anything?
That's a very good question. If you really want to understand twin reduction on groups, that is exactly the question you should start with. And I must admit, I haven't done that. As I say, the first thing you get is these, well, the very first thing you get is that groups that generate the same, elements that generate the same cyclic group are twins. So they go out first, but then new twins appear and other things can happen. Well, you can see how, M11, 7,000 odd elements, and it collapses down to just 300. So we're really, there's carnage there, twins all over the place getting thrown out. And I do not know what the real definition of that equivalence relation is, but I think you've really put your finger on absolutely the right question you should be asking.
Some more questions to Peter?
Is there any interest in starting with some particular graph and constructing groups that this graph arises in these different kinds of graph constructions you mentioned?
Well, I honestly don't know how to do that. I mean, I think the problem there is groups and graphs are very different subjects in a way. Groups are very tightly structured, whereas graphs are just floppy things that you can put edges anywhere. So starting with a group and getting a graph out of it, it's likely to be a nice graph. But starting with a graph and trying to go back to the group, mostly you're not going to succeed. So what you're asking for is, how can you direct your search to the places where graphs that come from groups are more likely to be? And I'm afraid I just don't know. I mean, it's something that really ought to be thought about, I agree. But I'm not really sure how you would do that.
Thank you. More questions for Peter?
One quick question.
Yes.
Can this difference graph be arbitrarily big in terms of number of edges?
Oh, I believe so, yes. If you take a huge group, then I think, twin reduction will only take you down. So, okay, let's put it like this. What you get out of the final result out of twin reduction is still going to have that group acting on it as a group of automorphisms. And so if you take a huge simple group, for example, there are lower bounds for the number of points that a simple group can act on. And so those lower bounds would apply to the size of the graph that you build from twin reduction. You might be nowhere near that bound. If you go back to M11, that's a group of order 7,920. It can act on as few as 11 points. But the action on 11 points is not going to have any interesting graphs because that action is doubly transitive. Any pair of points can be taken to any other pair. So either they're all edges or none of them are. So either you have a complete graph or a null graph. But you can't expect to get a graph that small that will come from M11. But on the other hand, we do have this nice one that comes from with 385 vertices. That's not too bad. Yeah, if you want bigger graphs, you can easily find them. But whether you can actually do anything with them is not entirely clear to me at the moment. Now, it's fairly early days on this. As I say, it was only 3 years ago that we had this research discussion, and everything's pretty much grown since then. But there are lots of good questions. I hope I've got that idea across. And what I really hope is that I've infected some of you with the idea that perhaps, there's something interesting to find here and you might like to have a go yourself. And please do tell me if you find anything interesting.
Peter, I have a question. Also,
yes.
Thank you for the excellent lecture. But I wonder, when you do when you do this process and you start with a simple group, let's say,
Yes.
and then you do the twin reduction and you get a graph, can you describe the cases where the new graph, so you then you look at the automorphism group of the new graph, then it's the same group that you start with. You have a few examples.
I hope it is at least the simple group and its automorphisms. I can't prove that.
I see.
And indeed, that's not always true because, okay, in my cases 1 and 2, you collapse down to a single vertex. The automorphism group of that is not the simple group you started with. In case 3, where you had 325 graphs, all isomorphic to K5 minus P4, well, the automorphism group of that, you can permute those components any way you like because they're all isomorphic. So the automorphism group has the symmetric group of degree 325 in it. So that's much too huge. So the answer to your question is that that's a test for whether we're in a nice, interesting case, whether the graph that we get has essentially just the group that you started with as automorphisms. So I had that M12 example where there were 2, you do twin reduction, you get down to 2 components, both fairly large, both over 1,000 vertices, but in each case, the automorphism group was just M12. So I think, in that case, I think it might be fair to say we found 2 interesting graphs out of that group. And it may be that as you go on, that's the sort of thing that will happen and you can get more and more interesting graphs. That's a possibility. We just don't know at the moment. This is, as I say, still experimental.
Thank you.
A quick question, the experimental part.
Yes.
Did you use a software for doing it?
Yes, I use GAP.
Okay,
That's software for particularly, it was invented to deal with groups, but now there are packages that will let you deal with groups and graphs together. One by my former colleague Leonard Seutzer, and that's what I tend to use. So that I find very convenient because you can easily program that to do twin reduction and then to find the automorphism group and other properties of the graph that you get left with at the end, find its girth and stuff like that. So that's how I do these calculations.
Fascinating.
GAP is a very nice program in my view.
Isn't Magma more powerful?
Yes, but you have to pay money to get Magma. GAP's free.
Yeah.
Anyway. I like things being free.
Yeah.
Especially since I'm just about to retire. I won't have anyone to buy expensive software for me anymore.
Right. Anyway, you find lots of interesting stuff. Thank you.
Yes. Yeah.
Okay. Thanks so much. I think it's a good time to stop. If you have more questions, Peter, be glad to respond to email. And
yes.
Peter, please email me the slides for posting.
I will do that.
Will be available in a couple of days. I will let you know.
Okay. Yes.
Thanks everybody for coming. And
I did spot one typo on the slides. I will fix that before I send them to you.
Okay.
Okay, but you will get them soon.
Thank you. Good night, everybody. And happy Halloween.
Good night. Good night.
Thank you.